Welcome for this session of the MOOC on New Space Economy. My name is Grégoire Bourban, Deputy Head of Space Innovation at the Swiss Federal Institute of Technology in Lausanne, EPFL, and I will cover the topic of satellite platforms. In the first slides, I will give a definition of what we understand by satellite platforms and provide some examples. Then, we will see why it is important and why we should consider it when defining a business model based on satellite infrastructure. We will finish with some ideas on future evolutions in this domain. The platform, or bus, of a satellite is the structure on which the payload, it could be a sensor, could be a scientific instrument, a telecommunication system, will be mounted. The trend is to develop standard platforms which can adapt many different payloads for different orbits. This can be seen as a core chassis in the automotive industry shared among different brands. Let's take the example of SwissCube, a student satellite developed at EPFL and launched in 2009. The satellite was developed as a one-unit CubeSat, 10 by 10 by 10 cm, a standard established at Caltech in the 90s. In the exploded picture you see all the subsystems of the satellite, from the structure, here the frame in aluminium, to the solar cells on each faces of the satellites, with the attitude and orbit control system, the onboard computer and the batteries inside the satellite. In the middle of this picture you see the payload, which was a small telescope. It was used to observe a phenomenon called air glow. Keep in mind the full satellite was 10 by 10 by 10 cm, so a very small and very compact setup. SwissCube was fully developed from scratch and integrated commercial off-the-shelf components to keep the cost low. Since then, a multitude of companies based their business on the development of parts for CubeSats. You can basically buy all your CubeSat in one of these one-stop shops. The total cost can be estimated at $100,000, but you still need a service behind, since building your satellite is not the trickiest part. Testing, commissioning for launch, and operations are important parts of the satellite life. The CubeSat philosophy changed radically what was usually done when building a satellite. Cost is decreased as you are taking more risks, using COTS components, non-qualified processes. But the yield, if you're flying a constellation, is still okay. And the beginning, the purpose was mainly educational, but as we will see, it changed quite a lot. As we have seen, usually the payload is only a fraction of the mass and volume of a satellite. Therefore, an optimization of the platform and its standardization are welcomed by end users, which are usually focused on the service to be sold to customers. Launch price is directly linked to the size and the mass of the satellite. We usually speak about $10,000 for 1 kilogram in orbit. But this price is decreasing with the evolution on launchers. But this is not only the important things. Having a standard platforms permits series production and cost reduction, but also an optimization of the launch capacity through the use of a dispenser. You can see here the example manufactured by RUAG Space for the constellation OneWeb, where the satellites are attached to the dispenser and separated once in orbit. Flight heritage of a standard platform is quite high, and is increased also the reliability by using this platform. For a CubeSat, the dispenser protects the satellite. It is a box around this small box of 10 by 10 by 10 cm. This permits to avoid some tests, such as the shocks, and it ensures the protection of the main satellite into the launcher. This will decrease the overall risk of a launch. I will give you some examples of platforms tailored to targeted applications. The first one is Iridium Next. Iridium is the first provider of a global communication system, also in the polar regions. Each satellite has a mass of 800 kilograms and is flying at an altitude of 780 kilometers. The full constellation has currently 66 operational satellites and was launched in between 2017 and 2019. The total cost of the constellation is estimated at $3 billion, which makes a few tens of millions of dollars per satellite. The second example is the well-known constellation Starlink. Starlink will provide low-latency broadband internet systems. Each satellite has a mass of between 227 and 260 kilograms, for roughly 1 cubic meter in volume. They are flying at an altitude in between 540 and 570 kilometers. In 2025, Starlink is supposed to be with 12,000 satellites in orbit, but they are looking for much more. The cost per satellite here in this example is roughly $500,000. The third example is Astrocast. One full session of this MOOC is based on this model. So Astrocast is flying nanosatellite, 3-unit CubeSat for Internet of Things services. One satellite is a 3 kilogram and 30 centimeter by 10 by 10 centimeter. They are flying at an altitude in between 510 and 530 kilometers, and they will have up to 100 satellites in 2024. Here the cost of the satellite can be estimated around 100 to 200 kilo. Prior to flying a full constellation, institutions like the European Space Agency, ESA, and the European Union are supporting the implementation of commercial in-orbit demonstration and in-orbit validation services. Customers who want to fly their payloads or test new technologies will have to manage only the interface with the satellite. In 2020, ESA and the European Union signed an agreement with the company Innovative Solutions in Space, IZSpace, to offer IOD and IOV service in space. Experiments will be integrated on board 6-unit CubeSats, and the operations after launch will be provided by IZSpace. We can mention also here the services provided by the company Space Applications and its service IceCube on board the International Space Stations, where you can basically run your experiment for roughly €50,000 for a 1 kilo experiment during a few months in the ISS. The platform Bartolomeo, also on the ISS, is provided by Airbus and exposed outside the station. And finally, the company Nanoracks, also providing IOD and IOV services. As we have seen, the development of standard platforms is driven by the satellite constellation needs, but once developed, it will be available for other customers. With the increase of computing power and the use of artificial intelligence, platforms are more autonomous, supporting more demanding applications. This will definitely drive new future business models. In summary, the consequences of the evolution of platforms are the following ones. First of all, it has enabled a new space by decreasing the cost along with the evolution of launchers and computing power. It has enabled new applications opportunities for new companies. And finally, the access to space is becoming more reliable as processes are streamlined.